Well, thanks for the introduction, and hello everyone. I see 19 at a test, so I don't know who you are, but anyway, good afternoon, if that fits for everyone. So we're going to talk about propensity score trimming here, and this essentially comes in two flavors, and I'll talk about this. And, I'll just start with a very brief introduction of propensity scores for those of you who may have heard about or attended the last seminars. So the propensity score essentially quantifies the probability that a person is treated given his or her observed covariates. So it's the probability of the treatment is 1 given the x, which is here a vector of covariates. The propensity score is estimated from the data very often using multivariable logistic regression, but other means can be used to estimate propensity score. None of these means have been shown to be generally superior to multivariable logistic regression, so I think that's still the standard method. The trick is that given the same propensity scores, and untreated, to have the same distribution of covariates used to estimate the propensity score. So every single person in your data set obviously is either treated or untreated, but have an estimated probability of treatment based on their covariates that has values between 0 and 1. And if you take two people, one treated and one untreated, with the same value of the propensity score, then we'll over a sample tend to have the same distribution of covariates and therefore are exchangeable with respect to covariates. So the treated and untreated will be exchangeable with respect to their covariates or risk for the outcome based on the measured covariates and conditioning on the propensity score, which then leads to unconfounded risk comparisons, risks. And risk differences gets a little bit murkier when we look at other measures of association. So how we do implement the propensity score once we have estimated the propensity score, we can subclassify on the propensity score by stratifying in quintiles or deciles. We do matching on the propensity score. Individual matching is most often used, which leads to exchangeable pairs of treated and untreated. Sorry for the old notation here. And that obviously applies to exposed and unexposed and other things. And do weighting. The most commonly used is inverse probability of treatment weighting, but you may have heard that there are other weights, for example, the SMR weight that can be used. And finally, we can just plug in the propensity score in our outcome model and control for a single covariate the propensity score as a continuous covariate. This is the least appealing of all the above because we need to get two models right, the propensity score model and the outcome model. So we need to correctly specify the propensity score outcome association here. So let's move to the trimming issue. And again, it comes in two flavors, and I'll start with the obvious one first, and then come to the other one. So this is the purely hypothetical distribution of propensity scores in the treated in red and the untreated in green. Now, obviously, you see that the propensity scores are higher in the treated than the untreated. That's because you're predicting treatment, but you also see that there are some values of propensity scores in the treated that are higher than the highest value in the untreated here, and vice versa, there are some propensity score values in the untreated that are lower than the lowest propensity score value observed in the treated. So when you go back to what I just said about conditioning on the propensity score, we can compare treated and untreated. It's obvious that in these regions here, where we have non-overlap, make a treatment comparison comparison, because for making a treatment comparison, you need both treated and untreated. So in this non-overlap region down here and up here, we cannot estimate the treatment effect without extrapolation of models. Therefore, we would like to exclude these people because they do not contribute information to estimate the treatment effect, and they actually pull the model because of extrapolation. So this is the trim of the non-overlap region, purely hypothetical here. As I said, the non-overlap regions do not contain any information to estimate the treatment effect. And not excluding these people leads to model extrapolation. The propensity score here is to assess the magnitude of this non-overlap, which is something that we would usually miss in the outcome model, and also to exclude these people. So the non-overlap, the dealing with the possibility to assess and trim non-overlap, is one of the advantages of the propensity score. This is a little bit strange wording here, but that's what I mean here. And thing worth mentioning here is that we are only interested in excluding systematic non-overlap. It may very well be that by chance your lowest propensity score value is actually in the treated rather than the untreated, and then we wouldn't call this non-overlap. We are only interested in the non-overlap that is systematic, not due to chance, essentially the treated with lower propensity scores, the lowest propensity score in the treated, and the treated with higher propensity scores than in the untreated. Okay, so training is important because in pharmacoepi, because we may actually have people in our data that have poor measured contraindications, especially when we're comparing treated with untreated. We often cannot clearly define who is our study population, who is everyone with the indication, and therefore trimming or the non-overlap region may be an indication for people in the population that should never have received treatment, and we do not want to estimate the treatment effect in these. So what different ways to implement propensity score? Here it is very important to realize that matching implicitly trims the non-overlap. So if I do match on the propensity score, I obviously end up with matched pairs of treated and untreated within the overlapping range of propensity scores, minus some issues about the caliper, which I think we can actually ignore here. When you look at this is real data from Medicare population, estrogen, over 65 initiating estrogen and initiating comparative drug, and you see that in the crude, we have almost 8,000 women initiating estrogen and 4,000 women initiating the comparative drug, but the estrogen initiators are younger than the initiators of the comparative drug. Now, after propensity score matching, you see that the age difference completely disappears. That's what we want to have. That's the exchangeability that we need to have to get to a valid treatment effect estimate. But you also see that we couldn't match all of the 7,800 initiators of estrogen, all of the treated here. We lost roughly 900 treated here because we couldn't match them to untreated because of non-overlap. So we do with trim of non-overlap when we do stratification, I think it's important to trim before we create quintiles or any quantiles, because otherwise you may have actually a very pronounced problem with non-overlap in the first and the last stratum of the stratification because of non-overlap. Overlap could easily be to an extent that if you don't trim for non-overlap before stratification, you end up with only untreated in the lowest propensity score stratum, only treated in the upper propensity score stratum, which would be a very strange, lead to a very strange analysis. Now, with weighting, it's a little bit more complex. So weighting, for example, inverse probability of treatment weighting, has the assumption of positivity. So you need positivity for these methods to be valid. Now, positivity is defined that you have a non-zero probability of reading any of the treatments that you're comparing for each and every covariate pattern that you actually observe in your data. So the overlap region clearly violates positivity because in the non-overlap region does have a zero probability of receiving either of the treatments that you're comparing in the dichotomous setting. So that result, however, and that's what John mentioned in the introduction, is not causal anymore for the whole population because you're excluding some people of the population. So we have a dilemma here that we cannot resolve. If we don't exclude the people, then we are violating one of the assumptions, and if we exclude them, we do not get what we want, i.e. causal estimate for the whole population. For inverse of treatment weighting, there are no clear recommendations what to do with the non-overlap region. If me, I would probably tend to exclude them, but I certainly know people who would not. The important thing here is with IPTW, people in the non-overlap region, and again, I'm only talking about systematic non-overlap, do not receive large weights. They actually receive very small weights because these are the untreated with the low propensity scores and treated with the very high propensity scores. So in reality, this is not a very big issue in IPTW analysis, and we all come to issues that are way more important with respect to IPTW in a minute. Modeling, again, because you have to get the you correctly specify the propensity score outcome association. Modeling is probably the analysis that's most affected by extrapolation. It is the least compelling because you have to get two models right. So I think in the setting of modeling, it would be also recommended to trim before you do the modeling. Stratification modeling, you would to actively exclude the non-overlap people in the non-overlapping propensity score range. With mapping, you do this by design, essentially implicitly. With weighting, it's a little bit a tricky issue here. And I want to point out is that the non-overlap region is obviously a function of how well you predict the treatment. So this is just a purely hypothetical example starting from the same non-overlap regions that we had before. And what happens if I add a predictor of treatment to the propensity score model is the curves will be more separated, and for I will end up with way larger non-overlap regions. If this predictor of treatment is also affecting the outcome, then it's a confounder, and then I need to put into the propensity score. But if it's not affecting the outcome, then it should not be in the propensity score. And this is another reason, or the main reason, why we should be careful of what variables we put into propensity score models, because we clearly increase the non-overlap region by putting in predictors of treatment. Some of them we need to put into the propensity score model, but we don't. So after the non-overlap region, so the trimming away of people where I cannot estimate the treatment effect, but that can actually harm my analysis, becomes something that I think is way more important, and that's what the paper that has been distributed is all about, and that's not trimming of the non-overlap, but within the overlap region. And I'll walk through these analyses, the results and the rationale to do these analyses. So this is the paper by Tobias Kurt that just still continues to teach us about weighing and propensity scores. This is an analysis on thrombolysis therapy coming from a German stroke registry. And thrombolysis is used in stroke patients to essentially decrease morbidity due to the stroke, but it has one traumatic side effect. It can lead to catastrophic intracerebral bleeding and increased mortality. And it has been shown to slightly increase mortality in randomized trials, but this is now an analysis of a stroke registry. And you see that only 200 people get treated with thrombolysis, whereas the majority of people do receive this treatment. Now, this is the table that finally stratifies the results by propensity score percentiles, ranging from 0 here to 100th percentile. And you see in each of the strata, and again, this is finely stratified, especially at the ends of the propensity score distribution, so these are not quintiles. You see the number of treated, the number of events in the group, the number of non-treated, the number of events in that group, the corresponding risk of death, and the corresponding odds ratio, the effect of treatment on mortality. And you realize that these are controlled for confounding, because the stratifying by the propensity score controls for confounding, as we learned. Now, the problem is that there seem to be some people here, and the other guys at the low end of the propensity score distribution, there's the mean score within that stratum, so they have very low propensities for treatment that got the treatment, these 17 people, and they have a very high mortality. And then up here we have some people who have a high probability of treatment, but who didn't get treatment. So these are the non-treated, and you can see that they have a quite high mortality, definitely higher than the rest of the people. The question is, why did these people receive the treatment? Why is treated contrary to what we predicted based on our propensity score, and do they have such a high mortality? So, example, this is a study done by Mark Lund et al. And published again in AJE in 2009. This is again a registry, this time registry of biologics from the UK, looking at the effect of biologics on mortality. Some signal there and we would expect that they have no effect or only a slight effect, increase risk for mortality. And again, stratifying by the propensity score, now from the lowest to the highest, than from the highest to the lowest. But you see here, these are the treated and these are the untreated, that there are some, here's not person, but a few people here who are in the highest propensity score stratum who did not get the treatment and have the highest mortality rate in the whole study. And again, why would these people not be treated according to prediction, and why would they have such a high mortality? Oh, I missed something here. Both data sets, the very strong heterogeneity of treatment effects, range from 0.25, so protective, to an odds ratio of 25, so a very strong increased risk of mortality. So this is clear in the heterogeneous treatment effect, and it's pretty monotonic over the propensity score range. And we saw the same or a similar thing in this study here, with rate ratios ranging from 2 to 0.24 here. Again, not absolutely, but quite monotonic. What do these non-uniform treatment effects over the propensity score and the observers treated contrary to prediction tell us? The non-uniform treatment effect could be real, so treatment could be more beneficial and less harmful in those most likely to be treated because they have all the indications and none of the contraindications. Again, absolute contraindications, but some variables steer you away from treatment. But it also be to unmeasured confounding that concentrated in those treated contrary to prediction, which would essentially explain why they treated contrary to prediction. So something that's unmeasured would explain why the treatment decision that we actually would have predicted was switched. So from treated to untreated and from untreated to treated. So we know that the propensity score is estimated on measured covariates. We know we have these patients treated contrary to prediction. So they're treated with the very low propensity scores and the untreated with the very high propensity scores. And a possible explanation, and again, this is in retrospect, seeing that they have such a high mortality, could be that someone overrode the expected treatment decision, for example, because they were very sick, very advanced stroke, and someone just said, well, let's try this as a last resort, or because they were sick to be treated, and treatment was withheld or declined. So it would be the untreated with a very high propensity score. It would be unmeasured confounding by prognosis and frailty, and you know that what we worked and people like Bob Lynn worked a lot on the issue of frailty, and we have several examples of this in the population-based data sets of the elderly. So, under the assumption, and this is a strong assumption, and I'll come back to that, under the assumption of confounding by, for example, frailty, a small proportion of patients at both ends of the overlapping propensity score range reduce unmeasured confounding. And I've used the cut points based on those treated contrary to prediction, the lowest percentiles of the treated and the highest percentiles of the untreated. It's an asymmetric trimming. It's not just a percentile of the overall propensity score that has been proposed by others, but actually a stratification of the propensity score distributions in the treated and the untreated. So choosing cut points based on those treated contrary to prediction, but I'm then excluding everyone who is above or below these cut points. And that would reduce unmeasured confounding under this assumption that we think is quite plausible in many settings, but obviously only a sensitivity analysis. So that's how it works. So we are talking about these people down here. They have propensity and are treated. And we are talking about these people up here. They have a high propensity and are untreated. So we're talking about the non-overlap region anymore. We are just talking about the edges of the overlapping region here. So what we have been proposing is if you increasing proportions here, and again you would base the cut point on the distribution of the propensity scores in treated, but you would put everyone below that cut point, the untreated and the treated, because otherwise you introduce bias. And we would do the same up here. We would choose a point based on the distribution of the percentiles in the untreated, but again would exclude everyone who is above that cut point. So this is the schematic of how this trimming within the overlapping range would work. So the simulation setup, it's a two-stage process as we hypothesize this process. So you have a predicted probability of treatment, and then something overrides this probability. This is predicted probability of treatment based on the measured variates that are available to the physician. And then there is something else here, for example, frailty, that would override this treatment decision in those at the ends of the propensity score distribution. So we use factors to be strong confounders, strongly affecting treatment and the outcome, as would be frailty. And you can see here, this is the stratified table from the simulation results, and you see that the leads to non-uniform treatment effect estimates our simulation setup, despite the fact that we simulate a uniform treatment effect of a relative risk of 2. There is some residual confounding in these here, and then see that at one end of the propensity score distribution, in this case at the lower end, we get treatment effect estimates due to last resort treatment. So that's the should not have been treated, but that got the treatment because someone thought, well, let's try this. This is opposite setting. This is the treatment withheld, very similar. So again, a uniform treatment effect with a relative risk of 2 is simulated, but we are estimating something below a relative risk of 2, and this even crosses the point of 1. So it looks even predictive here based on the last resort treatment. So some people who should have gotten the treatment, very high propensity scores, did not get the treatment, and these were at very high risk of having the outcome. And these are just some results summarized from the paper here. See that the unrestricted analysis inverse probability of treatment weighting and propensity score matching. So the restricted analysis shows a relative risk of 2.26. This is an adjusted analysis, but the truth is 2.0, and the estimates move closer to the true value of 2 by doing this trimming within the overlapping range. This here, the 0 and 100, is the trimming for the non-overlap. Anything beyond 1st and 99th percentile, and these percentiles is trimming within the overlapping range. See that matching is not so much affected by the last resort treatment. If you're estimating the treatment effect in the treated, the way that these extreme observations get is not as high as we get in the IPTW analysis. If you think about how the IPTW weights are calculated, so 1 over the propensity score in treated, it's easy to see that the people in the people with the lowest propensity score, close to 0 probability of treatment, get the highest weights because you're dividing by a very small number. Alternatively, the untreated with a very high propensity score, very high weights because you're dividing, the weight is 1 over 1 minus the propensity score, and if that propensity score is close to 1, then again the denominator gets close to 0, and by dividing something that's very small, you get very much weights. In the court example that I showed you, the highest weight for the highest propensity score, lowest propensity score stratum in the treated would be 2,000 if you calculate this out of the table. So these people would be 1,999 times in your analysis. IPTW is more affected by this. Matching is less affected because you're estimating the treatment effect in the treated. Results for the treatment withheld. So you see that the bias goes in the other direction here. So your treatment looks better than it actually is. Remember, the true relative risk is 2. So we start off with 1.31. And here, actually, the matching, the bias is even slightly more pronounced when the treatment withheld, because you're likely to match these people who are extreme observation on the high end of the propensity score with propensity score matching. But you see, by trimming within the non-overlap range, you come closer to the true relative risk of 2 for both IPTW and matching. Now, the simulations have obviously been set up so that this comes close to the true value here. That may not be the case in reality. So these cut points here are not written in stone. We just chose them. So the pattern here, what's happening to the treatment effect estimate is way more important than where it ends. So if it's moving, then you probably should add another with the 10th and the 90th percentile, for example, to see whether this continues moving, and the same would be applicable here. So it doesn't give you the true treatment effect. It tells you something about how treatment effect changes by trimming observations treated contrary to prediction or at the tails of the propensity score distribution, whichever you like better. So it's sensitivity analysis. Limitations here, unmeasured confounding is a plausible explanation for non-uniform treatment effects over the propensity score, but could have real treatment effect heterogeneity. In many settings, it's probably quite plausible that the treatment is more beneficial and less harmful in those most likely to be treated. To present all the results without trimming, the reader sees what's happening to the estimate, and then you have to give your interpretation of these. The study is obviously limited by the parameter space assessed, and as I pointed out, the cut points are completely arbitrary, and the pattern of the effect estimate, what it moves, is more important than actual cut point. An example, another example from a study of comparative effectiveness that we are currently doing within the UNC Design Center, and this is the risk associated with the new treatment based on IPTW analysis without trimming, with a non-overlap. It's trimmed for it's trimmed on non-overlap, no trimming within the overlapping range, and this is trimming within the overlapping range. And as soon as you start trimming, the relative risk goes from 0.5 to 1, and so. But that doesn't change anymore. So it seems like a 1% trimming would do all the trick here under the assumption that this is due to unmeasured confounding. Now, if you see something like that, obvious that you would try to look for a smoking gun, and we did so, and we found this patient here. The maximum propensity score, 0.97, this person was actually not treated. This is the perfect example for someone treated contrary to prediction. And you said, excluding the single person here, going from 144 people to 143, actually explains all the move of the relative risk estimate. Untreated person has the event, and because he is treated contrary to prediction, he receives a very large weight. The stabilized weight of 22, which is very high for a stabilized weight. The unstabilized weight would be way higher, and this contributes a large proportion of all and becomes influential. Now, it is an assumption that is some unmeasured confounding that would lead to withholding the treatment in this person, but we do not know, and therefore we have to present both results, which would be not easy to explain in such a setting as you can imagine. But what we did, obviously, also we tried to figure out, does this person have something that would explain why the treatment decision, the predicted treatment decision, was overwritten, and unfortunately we couldn't come up with something that would have explained this. Coding errors could easily lead to very large weights and treatment contrary to prediction, and there may actually be a way to identify such coding errors in your data set. So, coming to the conclusions here, unmeasured frailty may lead to non-uniform treatment effects over the propensity score. Trimming those treated contrary to prediction would reduce unmeasured confounding by frailty under this assumption. This would be used as a sensitivity analysis, and the results fully stratified by the propensity score would need to be presented if you have non-uniform effects, because again, this is an assumption that you're making, and people might not make that assumption or not be willing to make that assumption. And finally, the reduction of unmeasured confounding by trimming those treated contrary to prediction may actually be something that's to propensity scores, whereas other things that you do with propensity scores, you can also do outside of the propensity score as propensity score methods. So it may actually be something, because it directly deals with this contrary to prediction, that may be specific to the propensity score. My last slide, and it's just about the conclusions of trimming on propensity scores. So I think because the non-overlap region does not provide data to estimate the treatment effect, and regions violate positivity, and trimming overlap reduces model extrapolation. If these two taken together, I think in my book you should always trim for non-overlap. And this is, I think, the advantages of the propensity score, but you can obviously also trim for individual covariates outside of the realm of propensity scores, or you could trim on disease risk scores. So that's not specific to propensity scores, but the propensity score is an easy way to do that. There are consequences for propensity score variable selection, because if you do the trimming, you should definitely avoid variables affecting treatment but not the outcome. The so-called instrumental variables, avoid including these into a propensity score model, because they will increase non-overlap without any in confounding control. And I think we should always look for non-uniform effects over the range of the propensity score. If we find non-uniform treatment effects, then we present stratified results. We should use a causal overall estimator on standardization. This could be matching with or without replacement, or weighting IPTW or the SMR weights. Let's discuss residual confounding versus real treatment effect heterogeneity. And again, we should present this and leave it up to the reader, but we would also report sensitivity analysis based on asymmetric trimming of the tails of the overlapping range, as I just presented you. And I think this concludes my slide here. And the time seems to be pretty good too, so I'm open to answer questions.
Okay, Til, thank you very much for the presentation. I open this phone in just a minute to allow the audience to ask questions. Just a quick comment before you. I really appreciated your emphasis on the presentation of trimming. I know whenever you do analyses that people get really nervous when you start removing data or excluding people who might otherwise be eligible, and so that doing it in a very transparent way by presenting the overall result and then with in sort of a sensitivity analysis table showing what the effect is with different degrees of trimming. I think that's a very helpful suggestion. And also sometimes I like the way you focus on specific subjects who are in those tails, because sometimes there are interesting questions about that. That is, what might be the reason for the treatment contrary to expectation. And so I appreciate those features of the presentation. So can you open up the lines? Any?
This is Vincent Yao. Can you hear me?
Just barely. Can we get a little bit more volume, maybe closer to the phone?
Okay. Is this a little better?
Yes.
Great talk for the part. And I just had one question. If you have a limited data set, do you have any recommendations on how finally to stratify your propensity score results?
Not really, but I mean, you already gave the answer. Now, if the stratification, how finally you can stratify, will in the end depend on the outcomes you have. So, I mean, you need outcomes with a trader to estimate the treatment effect on the outcome. And, so it will in the end depend on how many outcomes you have, how finally you can stratify.
Okay.
This is Eric Smith. So it's a quick question. So if you do a quintile or decile analysis, and it appears that the risk is heterogeneous across your strata, that would essentially reassure you to some extent, right, that you probably don't have to go into great detail or worry about 1% versus 2.5 versus 5, or would you still do that as a matter of course?
No, I agree with you that's. I think, I mean, that what confounding at the end of the overlapping range would lead to would be non-uniform treatment effects. And if you don't see that, and we came up with the whole idea because we saw these examples of very heterogeneous treatment effects or non-uniform treatment effects. If you don't see that, then I wouldn't. Then this wouldn't speak the direction of assuming unmeasured confounding, at least not at the edge of the overlapping range of propensity scores, and then trimming wouldn't help you. If you have uniform treatment effects over your quintiles or deciles, then it's also easier to combine these into an overall estimate because you can use methods that do not rely on the assumption of uniform treatment effects, like Mantel-Haenszel, or using just dummy variables in your outcome model.
Thanks.
Any other questions? Right, Til, I have a question. I was thinking about that one could employ trimming in an automated kind of setting. That is, in a way, such as in a Sentinel system where you have maybe distributed data system where each of the individual sites are doing their matching of subjects and then pooling. Is there any thoughts that you might have on how trim can be implemented in such a setting?
Probably less than you have. I haven't been extensively involved in settings, and I think it would be hard to come up with an automated rule unless you just want to do 1% and the 2.5 and the 5% as we did in our simulations and see what happens. I mean, we've had examples with and Michelle Johnson-Funk published that from the in the HIV literature where actually the main part of the thing already happens before the 1%. So you would need to be more finely training on the 99.9 percentile. So I don't think you will find something that will always work, but you might very well be able to find something that will work 90% of the time.
Okay, that's very helpful. Thank you.
Susan Shortreed. Thank you. It was a very good talk, and I just wonder if you could make some more comments about the interpretation of these sorts of parameters when you're talking in a trimmed population. We may not entirely know who it is you're trimming and why, and how the interpretation might change.
I know why, and again, you usually would need to put these people into the table, and I think one great advantages of the Kurt's paper is he put up that table. Otherwise, we wouldn't know. So we know who these people are, and you can obviously even give more information on them than has been presented in that table. With respect to the idea that you're not talking the causal estimate anymore because you don't know to what study population your estimate is applicable. I realize the dilemma here, but if under the assumption that you have unmeasured confounding, the thing is with IPDW, for example, that you're clearly upweighing exactly these observations. So I tend to try to get the best estimate and sacrifice a little bit on the causality here, because it doesn't really help you to have a causal estimate that applies to the whole population when it's biased. I realize that other people have not the same view on this, so this is not something that's written in stone.
Thank you.
This is Alice. Idea about John's question, and then a question for Til. John, idea about your question is, I get that it's not possible to get the data from each individual site, so you have to run analyses separately for each site. One thing you could do would be to run propensity scores separately by site, and then aggregate that information and do some kind of sensitivity analysis to see what would happen if you assume that each site has the same this propensity score model, or if you assume that they're all different. The thought on that. Til, the question for you is about the asymmetric nature of the trimming. And I'm wondering, one thing about this is we don't know exactly how many observations we're excluding really 1% of observations when we go from 100 to 99. We're not excluding 1% of people. It's 1% of people in one treatment group and some different percentage in the other treatment group. And what if there would be any disadvantages? Another way I can think of to do it would be if I were estimating the effect of treatment in the population. Maybe I would want to trim the tails and then calculate percentiles for the whole sample and trim based on those. Or estimating the treatment effect in the treated, then I would look at percentiles in the treated on both ends. Would there be any disadvantages to that, or how would you compare that method to the one you described?
Well, that's good thinking. I mean, what we came from was that we wanted to focus on the guys who were treated contrary to prediction to find the cut point. Now, as I showed in this pure hypothetical, the figure there, by excluding just the percentage of the overall population within the overlapping region, you may not get to that people because these will be swamped by the people who are actually treated according to prediction. So at the lower end, any percentage that you choose based on the overall cohort will be driven by the untreated at the lower end and by the treated at the higher end. We wanted to focus exactly on the opposite, a specific proportion of those treated contrary to prediction, and I think that's the advantage of doing this asymmetrically. But I agree with you that we will, depending on the distributions of these, we will be excluding way more than just 1% or 2% of the people.
Makes a lot of sense to me. Thanks.
All right. So we don't have any more questions, and if not, then I'd like to thank Til for doing this presentation, and also again mention that the next one, March 22nd, is about adjusting for non-adherence. Thank you all very much.
Smith.